All right. Well, today I'm just going to go over a topic that's pretty darn important. Going to be the work energy theorem. Just going to go over kind of what that means really quick, just so you know, like a background of what this actually is, and then we can just get started in the lab. Let me go ahead and just share my little screen here. Okay. Right. Work energy theorem. Okay, so the work energy theorem basically states that any work done on an object will turn out to basically produce, well, how should I say it? Any work done on an object will give that object a certain amount of energy equal to the work done to it. Okay, so work done on some object, let's just say. Okay, so quite simply, that's what we're looking at here. So is okay. I see. Guys, two people said record. Yeah, I'm recording on my end. Is Marissa here? No. Okay. All right. Well, so as far as the work energy theorem is here, work done on an object equals the energy given to that object, so it could be equal to the energy that object has, depending. I didn't want to say that because something could already have some energy, and I could do some work on it, and then it can have more energy. So, one of the simplest examples is gravity, right? So work itself. Let's go ahead and let's define work. Work is defined as force times your change in distance. Okay. Thing is, work can only happen if you actually apply a force over a distance. Now, if I just push on a wall and the wall doesn't move, I'm just pushing on the wall. I'm not going to have an actual amount of work done. Okay, because I'm not actually traveling in any distance. Right? The wall doesn't move. We're assuming that this is a stationary wall in a house, right? If I push on that wall, because there's no delta x, no displacement, there's no work done. Okay, so that's what the delta x is. Now, force has to be some kind of applied force. It could be constant. It could be variable. But the product of those two things gives you amount of work done. Now, and Facebook things popping up. Work done equates to like energy of the object has after the work is done. And the reason why, we can look at the units here, is that force times distance is newtons times meters, which is actually joules, and joules is energy. Okay, and that is the units of energy right there. So a newton meter is a joule. Now, if you ever need to break apart, if you ever need to do unit analysis and you're working with energy units like joules, what you're going to want to do is equate that to newton meters, and then newtons are kilograms times meters per second squared. How do I know that? Well, because of, I'm going to put it right here, force is equal to mass times acceleration, so you can say kilograms times meters per second squared times meters, that's a joule. Okay? Either way, but so that's the units right there. But turns out that work, which is force times distance, is actually also defined as energy. And so, one of the more classic examples of the work energy theorem is raising an object a certain height above the ground. Okay, I can have some object here. I apply a constant force to it, just enough. Let's just say I apply a force that's just the minimum amount of force required to get that object to come off the ground. Right. This force here would have to be equal to the force of gravity on this object if I wanted to if I'm just talking about the barrier, like the threshold where the amount of force that I'm applying is just enough to where I could, a little bit more just makes it so that I rise this object off the ground, right? So I'm going to say that I'm lifting up on this object with its own weight and force. Maybe plus a little bit, but just basically as much as the thing weighs. Over a certain distance, right? So this is before, and then after it's up here. Okay, and it traveled some total distance of, I don't know, let's say it's 3 meters. Okay, so I applied this force, F sub g, oh my lord, spam, on this object over the course of 3 meters, right? Now, what this basically becomes is another work energy problem, except the work that we did to this object, what kind of energy does it have now, right? Because usually we're talking about something moving, having some kind of kinetic energy, but in this case, this object doesn't have any kinetic energy. Actually, the form of energy that it has now is gravitational potential energy, okay? And this is something that you may or may not have spoken about in class, but GPE, sometimes it's called, gravitational potential energy, is written as mass times gravity times height. Some of you may recognize that, some may not. Let's go ahead and look at the work done on this object, right? So let's look at the work done. So the work done is always going to be force over the change in distance, right? So the force applied here is actually the force of gravity, and the change in distance here is this whatever height this is here, h, which is 3 meters. So we'll go ahead and change that over. The force of gravity on this object, so like I said, I was pushing up on this thing with the same amount of force that it's pushing down on me. You would expect it not to move in that case, and you're right, but we're just going to go ahead and assume that it's like I got it started, and now I'm just applying that force on it the whole time just to keep it from going back down, right? So I kind of got it started, I'm just applying a little bit more force just to keep it going up, okay? So we'll just assume that the force I'm applying is equal to its weight. If I do that, okay, what is the thing's weight? Fg. Okay, Fg is the thing's weight. Fg is going to be its mass times the acceleration due to gravity, right? We talked about that a little bit. So we'll go ahead and substitute that into this expression here, and I'd get mg times h, which is just, mgh, which happens to also be gravitational potential energy, okay? So it turns out, just by doing a simple little force over distance here, I've found that the work done on this object by me lifting it is equal to the gravitational potential energy it now has, okay? So, in this case, the work is equal to its gravitational potential energy. Okay? So that's one little example of work, the work energy theorem. Another example would be me, starting something rolling from a stop, right? I can have some object just sitting there, not rolling or anything, stationary, right? Vi equals 0, initial velocity equals 0. Apply some force to it, force applied, right? Some distance later, I want to look at, okay, so it has some final velocity, let's see, let's just say it's greater than 0. I'm not even really going to do numbers here. I'm just going to kind of talk about the concept, right? So applying this force applied. Beforehand, this thing had no energy, right? Since it's sitting on the table, there's no gravitational potential energy here, and it's not moving, so there's no kinetic energy. So it's just sitting there, okay? In the next frame, actually, this force, accelerated this object to some final velocity, Vf. This thing's energy is actually equal to this kinetic energy. Let me go ahead and just get rid of this. Make it look a little better. Good. Get rid of my line. Okay. So here this thing will have an energy equal to the kinetic energy of the object, which I'll define now as 1/2 mass times this velocity squared. Okay? That's the energy this object has now. It's in the form of kinetic energy, energy of motion. It turns out that the work I did, right, so this thing started here, and it traveled to this location here. I'll call that just my delta x, okay? What I could say here is that the work, which is equal to that force applied times that delta x, it has to be equal to the energy that I put into the object, right? And that's the work energy theorem. The energy I put into the object, we found right here, it's this 1/2 mv squared. So it turns out that the work I did is equal to the energy put in the object, so I can say that the work is equal to the kinetic energy, or that the force applied times my change in distance is equal to this 1/2 mv squared. Now this is super important because this is going to allow you to solve a lot of different problems in physics. The thing here is that, you know, let's say I'm applying some constant force over some known distance. I don't know what the force is, but I know what the distance is, and I know what the final velocity is, okay? And I know what the mass is. I could find the force that I applied, okay? It's actually a very classic problem of the car braking. So, like, car's traveling has some initial velocity. It's just traveling along at the constant velocity, so you know it has a certain kinetic energy. And then over the course of, like, let's say 30 feet, it comes to a complete stop because of the brakes, right? They slam on the brakes and come to a stop in 30 feet, which is kind of crazy, but let's say that's what happens. Well, I know the distance traveled, right? And over that distance, there was a force applied. I know the original energy it had and the final energy, okay? So it had some initial energy, final energy was 0. So I know the change in energy, and I know that there was a distance over a force being applied over that distance. So I would say, you know, some force applied over some distance would equal my change in energy. And that's basically the work energy theorem, right? It's work equals change in energy, or delta E. Okay, work being, you know, force over distance. Now, we can kind of make this a little more calculus based, because the thing is, it's actually, like in the case of, let's see, with a linear force, or with a linear force, if we looked at a graph of force over distance here, it would just be some flat line over some distance, and then as soon as we stopped applying the force, it would go down to 0. Okay, and if we wanted to find the work, it would be force times distance, right? Okay, so let's use a question there. For question 3, did you guys multiply the hanging mass by 4? Let me get to that in a second. Okay, so work is change energy. Okay, linear force. Here we go. So work is change energy. Work is also force times distance. So if we look at this graph right here that I just made, which is a classic little force distance graph, you can see that the work being force times distance is actually going to be the area under the curve, again, just like we did the other day. The work will be right in there, right? Because this is going to be force is this side of this rectangle, right? And then distance is this side of the rectangle. And therefore, it's kind of like you're multiplying the two dimensions of the rectangle and making some area, right? It turns out the area under a force versus distance curve is your work. And like I said earlier, anytime you're given any kind of plot in physics, you always want to make sure you know what the heck the area represents, okay? So you multiply the y-axis and x-axis stuff together to get the area under the curve, and you want to make sure you know what that means. So for just a constant, I should say constant force, not linear force. For a constant force, this is what our plot would look like, okay? Now, You can have non-constant forces, so you can have variable force. You know, it doesn't have to be necessarily a straight line. I can have a straight line going up and to the right or something like that. I can make a triangle in here. Let's go ahead and just, you know, I'll just go ahead and write that one first before I go crazy here. How about linear? You see the force from the constant force section I just wrote here is also linear, but when I say linear, I just mean it's not constant, but it's also like not like, you know, quadratic. It's just going to be a straight line. So one of the most classic versions of that is a spring. And you'll see in the actual lab, if you read through the beginning part, which, you know, some of you may or may not do, it actually does talk about the force distance diagram for a spring. And a spring applies a force that's equal to kx, which is a constant times the displacement of the spring. So, or the separation from the separation of the spring from its natural length to its stretch length. Okay, but that's neither here nor there. So it's just a linear force, though. It changes with distance, but it's a linear force. So this would be my force applied up to the right like that. And what I would do is I can draw my little line straight down, and essentially this area in here would be the work done. Okay. Once again. And it's really the same thing. This is force. This is distance. You can imagine it like the base of the triangle is distance, the height is force, and you're just finding, you know, 1/2 area, or 1/2 base times height, and there's your force right there. So okay, so that's the work done. Again, is the area under the curve of a force versus distance plot, and it's a very important concept there. In this lab, we're relating all these things together, right? We're going to have this right here, this work equaling the kinetic energy. We're essentially using that in this lab because it asks, okay, find the energy using the velocity of this object. That's what they mean, use 1/2 mv squared. Find the, one of them says using that table A2, I forget exactly what it says, but this is using the area right here. So, you know, the area under the force versus distance curve is the amount of energy put into this object. So that's another part of it. And the last thing it actually has us calculate is, let's see. Okay, so yeah, so the program actually gives you this area, right? You'll see it in the tables. It'll give you the actual area under the curve, and that's what this value is. Another way to calculate it is to just take average force over distance, right? So this lab, you're going to equate 3 different values with a percent difference. The values are, let's see. Okay. Okay, so these are the 3 things that essentially we're doing right now in this lab. We're showing that the area under the curve is equal to the work done, equal to the change in energy. The average force multiplied by the distance over which that force was applied is also equal to the work, which is also the change in energy. And the final kinetic energy is equal to the work because your initial kinetic energy was 0, right? So it's really just, it's your kinetic energy final minus kinetic energy initial, which is equal to your work. But in this case, kinetic energy initial was 0, okay? So yeah, your final kinetic energy is going to be equal to your work. Right, and those are the 3 things that we're doing in this lab. And you can go ahead and get started working on that. There's just 2 sections to answer some questions there. You really just, you know, you're going to do this kinetic energy, which is 1/2 mass times velocity squared. Remember that it does say that you add the 4 stackable masses, so you got to use the cart plus the 4 stackable masses to get an answer that works there. Okay, so anything else I want to talk about here? The important concept to take away from this lab is this work energy theorem. concept here, though. The work done, which is force over distance, is equal to the total change in energy of this object, right? So, I've kind of given you a couple little example situations here. Now, okay, so you got some questions popping up. I'm going to go ahead and pull this lab up. Okay. So I'm going to go back here a little bit. There was a question from earlier. For question 3, did you guys multiply the hanging mass by 4? So let's see. Calculate the work done with smart cart by the pulley system using the equation driving theory. This shouldn't be a reason to... So for number 3, essentially what they want you to do... Now, it's kind of confusing on the... I looked through this already. It doesn't make any sense. I don't know who... There's not really a one specific equation they derive in the theory section for this. So that doesn't really make any damn sense at all. Oh, they're using this mm over the sum of the masses times g delta x. That's kind of crazy. Okay, so that's what they're using. Tension. Okay, mass of the hanger. Now, I don't believe that it should be 4 times the actual mass of the hanger. What's the procedure here? Yeah. It's a little silly using that expression, but we shall just go ahead and use that. This m sub h, m sub c divided by the sum of m h and m c multiplied by g delta x. That's just a fancy way to derive just force over distance, but okay. It's actually it's different from the last time I did this lab. Anyway, I'm not going to do the derivation for you. They do it there, and it's not really a big deal. You know, you would just do force over distance. So you wouldn't mess with all this. But, you know, work done, mass of the hanger, mass of the cart, plus the stackable masses, if it has stackable masses in it. Mass of the hanger plus mass of the cart times g times delta x. Remember, g is 9.81 meters per second squared. Delta x is whatever the displacement is. Okay, and then, yeah, this here is essentially the force, right? Why the hell? Okay, I did not verify that derivation. I don't know if that should. Maybe I'll verify that right now after I look at the other questions here. Okay, I'm coming down here. So from Nicholas, so for part A, number 1, do we just write down the given area in the curve? Yes. That's essentially what they're looking for, yeah. Use your area measurement in table A2 to find the work done on the cart by the pulley system. That's exactly it. You just write down that area under the linear force curve, or area under the constant force curve. What is the formula for work done on a spring to compress it? Oh, okay, so it depends on what context you're talking about here. We didn't really... Okay, formula for work done is going to be force applied over the distance. Now, the thing is, the spring's force changes constantly. So, what you're actually going to do is you're going to use this average force that's given to you. Okay, so, let's see, what part is it? Yeah, you're not going to actually have to do that necessarily Formula for work done on the spring compressed by length x. So work again is just force times change of distance. Now with the spring, okay, with a spring, F isn't constant. So it really boils down to work is equaling the integral from some first position to some final position of the force dx. Okay? Force for a spring is kx, so this would then be integral from some over some displacement, right? So x1 to x2 could be 0 to whatever the displacement is of kx dx. So that's 1/2 kx squared, evaluated from some initial to some final position. Okay, that right there is the energy stored within a spring. That's another expression. I didn't even talk about energy spring or springs of energy of springs. I didn't really talk about that at all. But you're not going to have to use that here. You're just going to go ahead and use the values given to you in the lab. So that basically just means use the equation from the theory section to go ahead and find what the work done should be for number 3 on part B, and write down the area for part 1. For part 5, calculate the final kinetic energy, and that's it. You don't have to worry about the variable force too much. Can you go over question 2, part A? What do you think would happen if the car was being pulled on both sides by equal masses? Well, what do you think would happen? Let's see. If you're being pulled on both sides by equal masses, that means really they're producing the same amount of force on each side, so it's being pulled in opposite directions with the same amount of force, right? What would happen? Very vague question. Nothing would happen, right? If you're being pulled in both directions with the same amount of force, you should expect that you're not going to move in either one of those directions. It turns out, because you're not moving, that you can apply all the force you want and no work is going to be done. Which is really what number 2 is trying to ask. It's like they want you to think about how much work is done if we're pulling on both sides of the same amount of force. And the answer is 0. No work is done because no distance is traveled. Okay? So that's basically question 2, part A. For number 5 in part A, do we use the total mass or just the mass of the car? It's going to be the total mass. For part A, we have the object that's experiencing that velocity is, it's the cart's mass, and it's got 4 masses on top of it. So the object is actually, the mass of the object is the cart's mass plus the 4 stackable masses. So yeah, number 5 we would use the total mass. For those who are inclined, calculus-based inclined here, or calculus inclined, I did a little expression on the page here, or in my notes, which is actually, it's good to know. This is really the most formal definition for work, right? It's the integral over from some starting distance, or some starting position to some final position of the work dx. Okay, the force dx. So you just put your expression for force in there. It could be some ugly expression that has all this dependence on position. If you're 3 meters in, you experience a different force than when you're 5 meters in, and it could be completely non-linear. It doesn't matter. You just shove it into that integral there, take the antiderivative, and then evaluate it between the bounds, and you've got your answer. Your answer could also be dependent on position, and that's fine. You'll know what your energy is or how much work has been done at each position. So, as is the nature with this lab, theoretically they'd be exactly equal. To answer your question, Hannah, they would be exactly equal, like in some perfect world. But in this lab, there's error, there's energy loss to like this. You hear the wheels move down the track, and the fact that you hear them means there's energy loss to that. And so nothing's going to be perfect in this lab. If you ever actually do get, like, if you're in a lab and you get exactly the same answer, then you should like maybe do it again just to make sure, because what you want in a lab is always, you want an answer that's slightly different. You don't want the same answer. You want there to be some kind of error, because if there isn't, then you did everything exactly perfectly, and it just so happened that I don't know. There's never a perfect situation. For part A, number 1, is it Just the area. Yes, exactly. It's just the area under the curve again. That's all it is. Number 6 of part A. Do we compare the two values by doing the percent error? Okay, so percent error. As a reminder here, percent error is call it like some value x2 minus some value, or let's not do that. Let's do we'll call it observed. Oh my God. Okay. That's what this one is. It's going to be whatever observed value you had, or experimental, minus theory divided by theory. 0.291 for number 1. Yeah. The area under the constant force curve is 0.291, so that's what that is, yeah. For question 1, go ahead and look at that. They want to see that your kinetic energy and work have the same units. Okay? Kinetic energy, we have an expression 1/2 mass times velocity squared. Well, let's see. 1/2 has no units, right? Mass is kilograms. Velocity squared, that's meters per second squared, right? The whole thing squared, so that's meters squared over seconds squared. Okay. All right, cool. That is actually like a kilogram times a meter per second squared times a meter, right? I'm kind of separating the meters. A kilogram times a meter per second squared, that's mass times acceleration, isn't it? Okay, so that means that this thing here is actually force times, or actually I should say newtons. Newtons times meters, okay? Which again is joules. Okay, cool. So we found out that kinetic energy is in units of joules, which we expect. How about work? Work is force times distance, which is actually going to be, newtons times meters, which again is, hey, look at that, that's joules. So cool, the units work out, right? The units of work are equal to the units of kinetic energy. As we should expect, since the units of work, since work is the change in energy, work is energy, the work energy theorem. Yeah, I don't need to talk about the spring one necessarily. I mean, it might be good to know. There's another form of energy. We talk about gravitational potential energy, kinetic energy. You can have spring energy or elastic energy. Spring potential energy. The expression for the spring potential energy, I think sometimes in your classes they might call it like EPE or something. Either way, I usually just call it U, but U is going to be 1/2 spring constant times the displacement from the equilibrium squared. Okay? Displacement from equilibrium means, you have some spring attached to a wall, like that's a relaxed position, but then let's say you stretch it all the way out to here. This distance between where it started and where it is now, that is your x. Okay, that is your displacement from equilibrium for the spring. That's the expression right there. That's how you found out. That's how you find out how much energy is actually stored in the spring. K is just a constant. that's given to you usually. Okay, it's a factor that tells you how strong the spring is. Okay, now you know, right? So you may not have seen this before, but there it is. Now I can go ahead and derive this again using the work energy theorem. I can derive it again using the definition for work. The work done for me to stretch the spring from this situation to this situation, that's what I want to find out, right? The work done there should be equal to the energy that I put into the system, okay? Work done, let's say work. Okay, work is going to be equal to the integral from some starting position to some final position of the force dx, okay? Force for a spring is equal to kx, okay? Now, the force that I'm going to be using to stretch this thing out would be equal to the force constant k times the actual distance I am from equilibrium. It's going to, so the amount of force I have to use is changing each time. Part B, number 1 is a displacement. No, part B. Given the fact that the force in the spring is nearly proportional to the displacement of the spring, which of the measured values in table B2 represents the spring constant? Oh, right. Okay. So, I guess I'll continue my little talk about springs here, and then I'll come. So just skip that for now, or you can listen to me what I'm doing here. I'll come back to that. Okay. Okay, so the spring constant is something we need to talk about, I suppose, even though this lab has really nothing to do with springs. I just kind of surprised you with the spring constant question. Or should I do that? Spring constant. Okay, let's do it now. So this has nothing to do with springs. I don't know why they even ask you a spring question. Okay, whatever. I did not anticipate a spring question. So spring strength is determined by this constant K. Okay. Now let's imagine for a second, if I want to get force from the spring's outputting, it's going to be, like I said, it's kx. Okay. We know that the units of x is meters. Okay. We know that the units of force is newtons, which means that the units of k have got to be newtons per meter, which makes sense because what k is saying is it's the strength of the spring, right? So it's how many newtons this thing outputs per meter of stretching. Okay, so that's what the K constant is for a spring, which is kind of not information you need right now, but I'm going to give it to you anyway because it kind of pertains to number 1. What are the units of the slope, right? In our expression for the spring force, the linear force, which is the spring force, you have force here, you have displacement here. So, okay. What's the slope? If you're trying to find the units of the slope here, what are the units of slope, right? The units of slope are going to be rise over run. In this case, rise is going to be force. To move up and down on the graph, you change force. To move left and right, to run on the graph, you change distance. So on the bottom you have distance. It's force over distance, right? It's newtons over meters, okay? Basically, what I'm trying to show you here is that the spring constant K, which is newtons per meter, is actually the same as the slope of my force versus distance graph, newtons per meter. Okay? So it turns out that the slope is equal to K. All right? And that is the answer to number 1. Which again, I forgot that they even ask any spring questions on this. Kind of takes you by surprise because it has anything to do with springs. But yeah, so there's your answer. Okay, he saw. Cool. Awesome. This is me just doing some little extra stuff here. So again, spring potential energy is 1/2 times that spring constant times the displacement squared. That's just an expression that, let's just say we've taken out of thin air because I took it from a physics book or took it from my head, right? Now, I can derive that. My initial position, let's say, was 0, xi, right? Let's say that xi just equals 0 and that xf, let's just say that equals x. I'll call it x sub d. Let's just say that this is displacement x, okay? So in u right there, I've said that's displacement x, and down here this is displacement x. So also force is kx, so let's see. This is actually going to be integral from 0 to some xd of kx dx, okay? The k is a constant, I can just bring it out, right? So I have k times the integral, 0 to xd of x dx. The integral of x is 1/2 x squared, so I have k times 1/2 x squared, right, taking the integration there. But that's defined from 0 to xd, right, which is then, k times 1/2 times xd squared minus 0 squared. And that's just essentially 1/2 k x displacement squared. Hey, okay, that was the work, which is equal to the total potential energy of the system. Again, work energy theorem, right? What you need to take away from this is understanding that the amount of work that you put into some object is the amount of energy change that object experiences. Okay, if it was sitting at rest and you just started pushing it, then the total kinetic energy that object has after you're all said and done is equal to the work that you did to it. Useful stuff, especially if you're solving physics problems. Like I said, the most common question that has to do with work energy theorem that comes up on a test is, a car braking, a car coming to a stop, right? You're given, the thing's velocity to start. You're given its mass. You're given the distance over which it took to stop, right? And because that force times distance is equal to the kinetic energy, you can equate those two things and solve for the force by dividing out the distance. And that's not something I feel like showing you right now, because you'll inevitably do that on your own some more soon. Okay, that's basically the whole lab, though. Yeah, you essentially just, the procedure is this. Number one, for part A, you write down what the area under the curve measurement is. What do you think happened to the cars being pulled on both sides? Nothing. No work's done. No energy change. It just stays still. Number three, calculate the work done on the smart car by the police system using the equation derived in the theory section. That's that weird mass over mass thing. Where is it? Right there. I have it in my notes here. MH MC over MH plus MC times G times the change in distance, which is really just, it's force times the change in distance, and that's just really going to be your average force. So it's kind of I don't know. It's you could also just have taken the average force value they give you and multiply over the distance, and that'll be the same. So, I didn't expect them to do this equation. Was not like that the last time I looked at this lab. So, okay. Anyway, that's what they wanted for number 3. Cool. Number 4, calculate percent error. Percent error I put up on the right there. So it's the observed minus theory divided by theory times 100. So here they're telling you, right, question 1 is going to be observed and question 3 is theory, okay? 5, using the final velocity given in A2. So the final velocity, you're going to find the kinetic energy, which is back here. I have it for you somewhere. Where the hell did I define kinetic energy for you? Did I even define kinetic energy? I mean, not really, but There it is. 1/2 mv squared. Okay. So that's number 5. You just find the final velocity, do 1/2 mass and velocity squared. The mass is going to be the mass of the cart plus the stackable masses on top of the cart, right? Because that's the total mass of the object that was moving. Okay, again, compare the values. Okay, you don't have to do a percent difference here for number 6. Just compare them. What do you see, right? They're going to be damn close. If they're not, then do it again. Number 1, given the fact that the force of the spring is linear proportional to the displacement of the spring, which of the measured values in table B2 represents the spring constant? It is the slope. Cool. Because of words that I said earlier. No, I'm just kidding. It's because of this good stuff right here, right? Requires some underlying knowledge of springs, which we didn't really even mess with springs yet, so it's kind of... Yeah. Was the value of the spring constant? That's the slope, right? So whatever you got for the slope, that's what the number 2 is right there for part B. 3, calculate the work done on the smart cart by the spring using the equation derived in the theory section. So you're going to go ahead and use that big ugly equation with all the masses in it, and that should give you somewhat correct answer. 4, percent error, area under the force curve from table B2 compared to the value predicted by theory in the previous question. So, yeah, your area under the curve from part B is going to be your observed, and then the theory is going to be question 3, whatever you got from question 3, and that's what you're going to do for your percent error for question 4 on part B. Question 5, part B, is using the final velocity, calculate final kinetic energy, and then 6 is going to be comparing those two again. You don't have to do a percent error there. You can if you want to. That's fine. But just, words and stuff. Words and things. And then for the questions at the end, I just want you to show me that. That's basically it. Okay. Kinetic energy is 1/2 mv squared, which is, kilograms times meters per second quantity squared. So that's kilograms times meters per second squared times meters, which is like newtons times meters, which is joules. And then work is force times distance, which is newtons times meter, which is joules. Okay. And I think I've covered everything I want to cover for work energy. Yeah. Whole bunch of good stuff. Okay. Yeah, I think so. I'm going to go ahead and just leave it open to questions now. These early mornings are a killer, huh? I'll tell you what, I am not a morning person. Okay, so I don't know if any of you are, but whoever you are, that whoever isn't a morning person, just know that like I'm right there with you. So yeah. Um, Monday the 6th, which is gonna be our last day. It's gonna be kind of like a maybe not like a short day, but I'm gonna be on a trip, leaving town on the 1st, and I'm coming back on the 6th. So on the morning of the 6th, we'll be leaving like later in the mornings after we do our thing. I'll be up in Santa Cruz, which is my hometown, and so it'll be like I don't know. I don't want to say it's gonna be half-assed, but it'll be maybe somewhat. You need to be blocked. Okay. Alright, so there's still quite a lot of you in here, so just post whatever questions you have whenever you have them. um, yeah. I'll be right back and I'll see what you guys posted. The anticipation's killing me. Okay. Let's see. Number one in the questions section is actually pulled up on the screen right now, Caitlin. I don't know if you saw it. Um, Essentially, they just want to see that the units of kinetic energy is the same as the units of work. And so that's what I did right there. Question one. Yeah. Kinetic energy is 1/2 mv squared. Um, yeah. You see it. Kilograms times meters squared per second squared, which is kilograms times meters per second squared times meters, which is newtons times meters, which is joules, and then work is the same thing. Yeah, and you get, the way I remember all those conversions is I remember the equations, right? So, force being kilograms times, or force being mass times acceleration, that's kilograms times meters per second squared, and then that's how I was able to see that there is a kilograms times meters per second squared right there. And I was like, oh, well, that right there must be, I was able to pull out that extra meters there, and that's a Newton. Peach. Kitties. Hey. Take that shit. All right. I think I'll go ahead and just end the recording since we're right there at the end.